So now let us see how can we go from something that is completely random to a classifier that would really do the job that we want. That means classifying different images correctly by using a loss function. So remember that a loss function is something that will have a high value, so a large value when we are not going in the right direction, and a small value when we have a good estimate of the classifier. So because we have this this function that gives us a measure of how bad we are right now, and we want something like that, we can minimize the loss function by using the space of parameters. What that means, we are going to take every parameter of the model and then compute the loss function using those parameters and see what happens when we change those. So for each dimension, what I'm going to compute is the derivative. So this is the definition of the derivative. Is the limit when we get a very small delta value, and then we change x in this case, and then compare it with not changing. So let's say we have a function f of x, and we compare that with a function f of x plus some delta. So this will give us the rate of change. Trying to go with in this case with the loss function, that is when we are when compute the derivative of the loss function, we do that by using a parameter w, or a fixed parameter. In this case I'm using w, but also the bias terms should be implemented in that way. So I'm going to compute what is the loss over how the loss changes when I change one parameter. I'm going to go back a little quick just to show you. So when we have this output here, what if I change this first w here? If I change that, what would be the effect on the loss function? This is what I'm measuring. So this is done by summing a very small value in w and then computed the difference when I don't have that. Because we have multiple dimensions, in this case here, sorry, I'm going back again. In this case we have a 3 by 4 matrix, so 12 parameters plus 3. So we have 15 different dimensions that we have to compute. And I forgot to mention that the dimensions of those are dependent on the class, on the number of classes and the input data. Because we have just 4 pixels and 3 classes, this matrix here could be 3 by 4. And the bias 3 because we have 3 classes. Right? So in this case we have 15 dimensions. We have to compute the derivative for every one of them because we have a gradient, a vector of derivatives. We may use a numerical gradient, which is an approximate of the analytic gradient, which is the exact solution. However, the analytic version is often not available, or is very hard to estimate or to write. So we are going to use the algorithm well known that is called the gradient descent. This algorithm search for the value of the function. Remember that you want to minimize it, moving in the direction of the negative gradient. So let's say we have a parameter w, and because we know the loss function, Let's say I know all loss function, all values of the loss for every choice of parameter w. So this is kind of like an impossible scenario, so I'm just showing you for visualization. But let's say that I know, just for visualization, I know the shape of this function. So this is the squared error loss. This is a convex function, so very well behaved scenario. But in fact, when I'm computing the loss, I don't know this shape, right? So I just know one point because I can compute just one point at a time. Let's say I started by drawing w randomly and it came -1. Okay, so forget about this plot for an instance. I just have w equal to -1. What I want to do is, well, I can have to compute the error or the loss function, in this case the squared error loss. So this is the loss function. When I compute that, it gives me this point here. This point is 7 or around 7. That means my current loss is 7. When I choose -1, my loss is 7. How can I improve that? I compute the derivative, and the derivative is drawn. The tangent line here is drawn using this dashed line. This means that the derivative is negative. It's because the slope here is negative. So what would be the best choice? If I know that the derivative is negative for the parameter w, would I be in a better direction to sum something to w or subtract something? Should I go on the right hand side direction or the left hand side? Well, if I go for the left hand side, so that means if I decrease w, I'm going to climb this loss here. I'm going to end up with a higher loss. I don't want that. So I want to sum some value. That is why we use the negative of the gradient of the function. So we often go in the direction of the negative of the function. We are going down this here, and hopefully we'll end up here on the lowest value, the minimum value. But I'm going to do that for all values of w. Let's say we organized w or matrix here in a series of values, and then we just sum a small value and then compute the derivative. The first case here, so we can see here, so with choosing original w, we have a loss of, let's say, overall loss of 2.31. But by choosing, moving a little bit the first one, what we have is 31,201. That means we improved a little bit. So the derivative is like that, is negative. That means if we sum on this first parameter, we are in a better shape. And we do that for every parameter. So for the second parameter, if the derivative is 0, that means the loss is unchanged. We are probably in a local minima for this parameter. It can change in the next step, but right now is what we have. And if the derivative is positive, we probably have to go back. So instead of summing, which will in this case here increase the loss function, we are going to take the negative of that and then try to reverse this direction. And then we can do that for all parameters. And in this case here is just an example. By going in the right directions here, also in the negative of the gradient, I was able to improve the loss a little bit from 2.3 to 2.08. But as you can see here, this type of approach is slow. It can take a lot of time to compute all those derivatives or those gradients. And remember that I'm doing this for a single image, just one image. So if I do that for all images in a data set, and the data set has, let's say, 1 million images, well, probably may wonder how much time would that take. It will take a lot of time. So we have an approximate algorithm that is called stochastic gradient descent. And the name looks fancy, but it's very simple. The idea is, instead of using all training images to train or to adapt the parameters w, so to adapt here the parameters w, we are going to randomly draw a mini batch of instances. What is a mini batch? It's basically a small set of images. Let us say that I defined it at 16. So instead of using one image to compute the derivative, I'm going to use 16 images. So I'm going to compute the loss for 16 images, get the average of that gradient, and then use that gradient to adapt all values of w. So I'm doing just once, and I use 16 images at a time. But note that I'm using an average of 16 images, and this will make it much faster. Okay, yes, it is much faster, but it gives bad estimates on each iteration. So therefore, we often need more iterations. But even though we have bad estimates and we need more iterations, it's worth doing SGD instead of the regular gradient descent. You will see in the literature people using from 16 up to 512, so 512 values or instances in the mini batch. And we will note there is a power of 2 obsession in this case, so people will use 16, 32, 64, and so on. 32 is often the standard choice for many algorithms. However, this can significantly impact the result, so you have to at least try and test them. So search for the best batch size. This is important. However, this will be something around that, probably. Okay, so on the next video I'm going to show you, now that we have all the tools, so we do have the knowledge on what is the problem, what are the functions that we want to learn, that are basically functions on the form wx plus b. And then we have the algorithm, which is the SGD, and we also have the optimization function, the loss, and we understand what we want to achieve. We can now build a simple network.